So today's lesson, we're going to look at the difference between what we call a real gas and an ideal gas, and we're going to learn how to solve some problems. So let's start with real gases. So a real gas is exactly what we say, what we would find in real life. All right, these guys are subject to intermolecular forces. All right, so they do have intermolecular forces, and that is inter, not intra. All right, and if you'll remember, this is an attraction between particles. They are able to liquefy under extreme pressure. They have volume. And conditions in which real gases exist are going to be high pressure and low temperature. Okay, so why do real gases exist under high pressure? All right, particles are very close together under high pressure. If we increase pressure, then we are pushing those particles much closer together. All right, so when particles are closer together, they are more likely to have interactions with each other, and therefore those intermolecular forces coming into play. Under a low temperature, they have a low kinetic energy, meaning they are moving slowly. All right, so if they are moving slowly, then they are more likely to interact with each other and again have those interactions a intermolecular force coming into play. Okay, so real gases, high pressure and low temperature. The reality is, though, the majority of gases behave as what we call ideal gases because gas particles are very far apart. All right, so gas particles are so far apart from each other, under most circumstances, they will behave as an ideal gas. All right, and this is going to be some conditions for this is going to be low pressure, and high temperature. All right, so under a low pressure, particles are going to be much further apart. They are less likely to interact with each other, and therefore no intermolecular forces coming into play. A high temperature, they are going to have a rapid random motion. All right, they have a high kinetic energy and a rapid random motion. So they are more likely to zoom past each other quickly enough that the intermolecular forces do not come into play. All right, so ideal gases are going to behave under the assumption of the kinetic molecular theory. And I'm going to abbreviate this KMT. So anytime you see KMT from now on, we're talking about the kinetic molecular theory. All right, so what does the kinetic molecular theory state? The kinetic molecular theory states that gas particles are tiny particles and they are spaced far apart, which we know to be true. It states that particles are in constant motion. It states that we have elastic collisions. All right, so what is an elastic collision? An elastic collision is when we have a collision between two particles, then there's not a loss of energy. All right, so we're basically saying they collide and move on without a loss of significant amount of energy. They have no intermolecular forces. And again, this is inter, not intra. And the kinetic molecular theory, or I'm sorry, the kinetic energy, the kinetic energy is going to depend on temperature. All right. So the kinetic energy, again, is the energy of motion. All right. So the higher the temperature, the faster moving the particles are, and therefore the more kinetic energy that they have. So we can use our ideal gas law formula, where PV equals nRT. P is the pressure. V is the volume. N is the number of moles. R is our gas constant. And T is in temperature, or T is temperature. Now our gas constant is on our reference tables here. So here's our gas constant R, and you'll notice that we have 3 different gas constants. Each one has a different unit for pressure. So we have atmospheres, we have millimeters of mercury, and we have kilopascals. So we can solve for all 3 of these different units. Notice our volume in the gas constant is in liters. So our volume has to be in liters. And our temperature for the gas constant is in Kelvin. So our temperature is also going to have to be in Kelvin. Now, there is a shortcut. We're not going to learn the shortcut. We're not going to ever mention the shortcut again. I don't teach the shortcut for this reason. What I find is when I teach the shortcut, students start using it incorrectly. I start seeing the shortcut for the craziest things. Students start using the shortcut to try and convert things into grams and into ions and into atoms, and it just simply becomes a hot mess. Y'all use it for everything. So we're not even going to learn the shortcut, because the reality is if we do the ideal gas law, it will get us to the answer 100% of the time. So we're going to stick to a formula that will get us there 100% of the time, and not try and learn when do I use the shortcut, when do I not use the shortcut. This is way easier. Okay, so we're going to stick to that. I don't ever want to see the shortcut. We're not even going to mention it again. We're going to pretend like it does not exist. All right, so let's do some practice problems. If I have 0.075 moles of carbon dioxide that are produced by a reaction of acetic acid, which is vinegar, and baking soda, a temperature of 5 degrees Celsius and 0.921 atmospheres, what will the volume of the gas occupy? Okay? So here's our formula, PV equals nRT. All right, where my pressure is 0.921 atmospheres. We are looking for volume. My number of moles is 0.0750. My R. My volume here is my pressure here is in atmospheres. So I need to find a gas constant that also has atmospheres, which is my first one, 0.0821 liters per atmosphere divided by Kelvin mole. And my temperature is 5 degrees Celsius. Again, my gas constant is in Kelvin, so I'm going to have to convert this into Kelvin. So 273 plus 5 is 278 Kelvin. And if you're not sure where that number comes from, you may want to go back and review our changing pressure and temperature video. All right. So when I plug this into my calculator and I solve for volume, all right, go ahead and just plug it in as one big formula. All of this multiplied in parentheses divided by 0.921 atmospheres, and we find our volume of 1.86 liters. Again, we're using the rule of three. All right, rule of three. Let me just take a moment and let me just show you guys with just the units how it does in fact cancel out to liters. So let me start here. I have atmospheres equals moles times liters times atmosphere over Kelvin mole times Kelvin. All right, mole is on top, which cancels mole on bottom. Kelvin is on top, which cancels Kelvin on bottom. So now I am left with atmospheres equals liters times atmospheres. And I did divide both sides by pressure, which was in atmospheres, leaving me with liters. Okay, so you can actually figure out your units based upon your cancellation. All right, let's look at number 2. If I have a 150 mil sample of hydrogen gas, the pressure is 740 milligrams of mercury, and my temperature is 22 degrees Celsius. I want to know the grams of hydrogen that have been collected. All right, so here's my pressure, 740 millimeters of mercury. Here is my volume, which is 150 milliliters, so that is 0.15 liters. N is my number of moles, and we have learned how to convert moles into grams, so I'm going to solve for moles first. My R, I need to find a gas constant that has millimeters of mercury in it, which is my second one, 62.4 liters times millimeters of mercury divided by moles times Kelvin. And my temperature is 22 degrees Celsius, so when I convert that into Kelvin, that is 295 K. So when I solve for my number of moles here, I plug this into my calculator, I find that I get 0.00603 moles of hydrogen. Now, my formula asked me to put it into grams. So now I'm just going to set up a dimensional analysis where moles of hydrogen goes on bottom. I can go direct to grams using the mass from the periodic table. 2 hydrogens has a mass of 2.02, and that will equal 1 mole. So when I plug this baby into my calculator, I get 0.012 grams of hydrogen, and we're going to follow our rule of 3 here. So let's add a 2, 0.122 grams of hydrogen. Okay, so our final problem. A sample of gas at STP contains 15.8 liters. How many moles are present? So we are at standard temperature and pressure. Standard temperature and pressure. I know my standard temperature is 273 Kelvin. My standard pressure, well, I'm going to choose a standard pressure, whether it be atmospheres, millimeters of mercury, or kilopascals. Let's go with kilopascals because we haven't used this gas constant. All right, so my standard pressure for kilopascals we have learned is 101.325. My volume is 15.8 liters. All right, how many moles are present? That's what I'm looking for. My gas constant for kilopascals is 8.314. And my temperature, it's standard, so that is 273 Kelvin. Again, plug this into your calculator as one problem. This is your numerator, put it in parentheses, divided by this, which you're going to also put in parentheses, okay? So when you plug this into your calculator, you find that N equals 0.705 moles. So let's just take a moment and let me prove to you that it really does not matter which of these you use, okay, because standard temperature and pressure. So let's go with atmospheres. I know that the standard pressure in atmospheres is 1. My volume is still 15.8 liters. Well, I'm looking for moles. All right, so I'm going to use 0.0821. And again, my standard temperature is 273. So when you plug this into your calculator, what do you get? You still get 0.705 moles. All right? So as long as you line up the correct pressure with the correct gas constant, if you are at STP, it does not matter which one you choose, you end up with the same answer. And if you really wanted to, you can go ahead and redo this with the millimeter of mercury one using your standard 760 millimeters of mercury and see that you will also get the same in value.